right, thank you. If you can't hear me, just shout and I'll speak louder into the mic. That's my name. I work for Gawa, and like with most people with bad opinions, I have a Twitter account. So you can listen to my bad opinions if you want. Okay, so overview, what is it we're going to talk about? We're going to talk about FHE, which stands for fully homomorphic encryption. We're going to talk about what is it exactly, how does it work. Then we're going to talk about symbolic execution, which seems unrelated, but I'll explain why they're related. And then we're going to talk about, well, what's that? And then you can ask me questions. Okay, and then we're going to talk about how it all relates to Julia. Okay, so there's lots of data in the world, and in particular, there's lots of private data. And data scientists are very good at doing computations on the data, but sometimes privacy isn't the foremost concern, and that can be a problem. So let's say I wanted to have my genome sequenced. That can help me to know if I'm susceptible to any particular disease or my genealogy. But if left kind of in the open, it can also be dangerous, right? Because people then have information about me. It may not seem immediately obvious how your genome can be used against you, but it can. So currently, what you do is you pay a company, and they take some of your DNA and they sequence your genome, and then they provide that genome to a possibly different company that computes whatever function. In this case, the function you care about is, do I have some disease? And then they give you the answer. And what's the problem there? Well, you may trust the genome sequence company. You may trust them, right? That's why you're giving them your DNA. But you may not trust this cloud provider that tells you, has the analytics that says, do you have this disease? What if they don't encrypt their data? Very common problem, right? People have all sorts of private data just kind of unprotected in the cloud, unencrypted. So what's the solution here? Well, lots of companies do this. What's the thing that's missing? Okay, security. So what I want is to be able to ask these questions about my private data, but I want to be able to do it with the assurance that my data is secure. So currently, the way people deal with security is you have access control, you have perimeter security, and then also you have encryption. The problem with encryption is sometimes you have to decrypt the data to make it useful. And then in that, when it's in plain text, it's just as vulnerable. So what are we going to do? We're going to use some fancy cryptography to solve this problem, because fancy cryptography can be fun. Okay, so fully homomorphic encryption, what is it? Well, what it is that it allows you to compute over encrypted data. So you're able to compute functions on data without ever decrypting it. That may seem like, whoa, how's that work? And the answer is a lot of cryptography and math. So we're not going to go over those details, but it's actually quite cool. There's private key encryption, just quick overview. And in order to encrypt and decrypt data, you use the same key. The danger there is that then if you want someone else to use your data in some way, they now know your key and can encrypt or decrypt as if they were you. So the solution to that problem was public key encryption, and this is a lot of the encryption we use today. And it allows you to use different keys. So you can have a private key and a public key. And someone can encrypt something with your public key, and only you can decrypt it. And that's pretty powerful, right? So you can say, I trust you to encrypt my data, but once it's encrypted, no one's able to unencrypt it. Fully homomorphic encryption is a public key encryption that allows computing over the ciphertext, allows computing over encrypted data. And what's cool here is, as we said here, this F, this function, this pointer doesn't work, it can be arbitrary. Now, there should be a big asterisk there, because arbitrary is true, but some things are really, really expensive and take a lot of computational power to do. So it's not the performance of the function as it was unencrypted, and then the encrypted version isn't necessarily a one-for-one kind of exchange. That being said, you can compute arbitrary functions. Okay, so now let's go back to our sequencing the genome and having someone tell us something about our genome. But now we're going to do it in the context of FHE. So now I still pay the company, and I give them my DNA, and I say, once you have the genome, encrypt it with my public key, right? And now what they do is they send the encrypted genome to some cloud provider. So the cloud provider doesn't have your private key, so they can't unencrypt it. And you ask, OK, do I have some disease? Can you tell if I have a disease from my genome? And they do the FHE computation over the encrypted data. And now they have this encrypted result that they don't know what it is, and they send you the encrypted result. And then you say, OK, well, I have my private key, and I can decrypt it, so I know the answer. So this is really cool, I mean, in my opinion. And I think it's very powerful, and it allows for a whole new way of looking at privacy. So in this case, we're talking about genomic data, but we have people interested in using this at the census, so that only analysts can compute over the census data, but without having to have that data decrypted, right? Which is a really big priority at the census, because they're worried of people using census data irresponsibly or improperly. Okay, so FHE currently provides two main operations over encrypted data. So it allows you to add two things, and you get the resulted sum encrypted, and you can multiply two things, and you get the resulting product encrypted, and that's it. So you can have functions that sum and multiply and have the encrypted result. And we treat this as an arithmetic circuit. So that's going to come back later. You have a circuit of these things, and you can do it all encrypted. OK, where's the hitch? So far, I've painted this really rosy picture. Where's the problem? OK, the problem is that FHE is really, really hard to program in. So our work is trying to make that easier. So currently, if I wanted to add three numbers using a state-of-the-art FHE library in C++, it requires all this code. And this is not exaggerated. This is the code as published in the paper where they show this work. So this is how they think. Look how great it is. So it's a lot of code to add three numbers, and that's not anyone's fault. It's a complicated thing, and sometimes complicated things are hard. OK, well, our work says, OK, let's write a compiler. So at Gawa, we're programming languages people. So our hammer to every nail is write a compiler to the thing. So we take Julia code, and this is the code computing the same thing. So it's still, you still have some overhead, some boilerplate, but we think it's much better. And Julia is a little more pleasant to work in than something like C++. So there you go. That's the goal. So we have this package, fhe.jl, and we wanted to make it as simple as possible to use FHE. So there's an API, allows you to generate keys. You can encrypt data, decrypt data, evaluate Julia functions over that data. There's two underlying libraries that are necessary for this. One is Palisade, and that's the actual execution of these encrypted arithmetic circuits. And then the other is Crucible, which is what we use to compile Julia to these circuits. So quick aside, Palisade, it's written by some folks at the New Jersey Institute of Technology. This performs the actual FHE computation. So this is what's actually doing the kind of hard cryptographic work. But on top of that, excuse me, it also manages what we call a crypto context. So like your key pair info and other related like metadata about your computation. And overall, it makes using FHE much easier, but it's still not something you'd want to program in directly. So our job is to make it so that you can just program in Julia, and then this does the heavy lifting behind the scenes. So here's kind of just a quick workflow of how it might work. On the left, you have kind of the Julia environment that you're in. It could be the REPL. And you can when you evaluate a function over encrypted data, the Julia REPL serializes the AST, sends it to a cloud service that then turns that into a circuit, runs that circuit over the encrypted data, and sends you back the encrypted result. And then that's now available in your Julia REPL. So pretty cool. OK, but how does compilation work, right? I'm talking about these circuits, and you can only add and multiply. Julia programs do a lot more than add and multiply, right? Well, that's where symbolic execution comes in. How do we do symbolic execution? I mentioned there were two main libraries. Palisade does the FHE part. Crucible does the symbolic execution part. So it's a symbolic execution system written at Gawa. It currently supports LLVM, so that's one of its main uses. It symbolically executes LLVM for program verification. And now we've kind of extended it so it can support Julia as well. We use it in this project for fully homomorphic encryption, but symbolic execution is actually much more general. So it can help you reason about program equivalence or learn safety properties of programs or where programs might go wrong. So symbolic execution in one slide. Let's try. So you treat certain program variables as symbolic variables, which just means like they're abstract, they're just like a placeholder, they don't have an actual value. And then for each path in the program, so wherever control flow would change, you keep track of what that means about the symbolic values. Like if you have a if statement, is a symbolic value used in that if statement? And we call that a path condition. So in each path of the program, there are certain constraints on the symbolic values. And now each possible execution of the program, because by its nature each path represents an execution, you can identify it by its path condition. So really quick example. Let's say we have this function, and it just does an if, an else if, and assigns things to A. On the right, this is how you would symbolically kind of execute, kind of in a very hand-wavy manner. At each branch, you would keep track of was x less than 0, greater than 0, and then that would tell you something about the state of the program. So let's look at some example path conditions. So here we have if x is greater than y, then the state of the program is such that in your state m of p is valued y, m of q is valued x, right? We also have this one where if x plus y is greater than 5, that's some condition. If that's true, then m of p is valued y and m of q is valued x. And then you can have conjunctions of these path conditions. So here it's the same as above, and you have kind of its inverse. If x is not greater than y, then it means something else, right? So from these path conditions, you can reason about what the program state is. Okay, so we have these path conditions. We did the symbolic execution. What now? We can generate a circuit that, given the inputs for those symbolic values, so for those things that we treated as abstract, now we have a circuit that if you give us values for that, you get the output of the program. So in a sense, you can think of symbolic execution as kind of getting rid of all the execution you can do except for the parts you kept abstract. And that's why you're able to do things like represent it as a circuit that only has multiplies and additions, because you've kind of gotten rid of the loops. You've gotten rid of the if statements. You've gotten rid of a lot of these other constructs. And then all you're depending on now are the values you kept abstract. Okay. And then this leaves us with a really big bonus, right? So earlier I alluded to this, but I wanted to highlight it. The equivalence of circuits is easier than the equivalence of arbitrary programs. So once we have these circuits, we can actually do things like, I changed my program. So at first I was writing a Julia program for linear regression, and I kind of wrote it in a naive but clearly correct way. And then I wanted to optimize it, so I tweaked the linear regression code. But did I change the meaning? Did I change the semantics? Or are the programs equivalent? And we can actually use this for a large portion of programs to determine whether yes or no. It doesn't work for all programs, but it can tell you yes, no, or we don't know. Okay, so really quick demo. Okay. Can everyone see that? Yeah? No one said no, so I'm going forward. So this is just a Julia file where we are using the fully homomorphic library that we've made. So let's just walk through what's going on. So I mentioned these contexts. So here I'm saying I want a context that encrypts the data. So the alternative would be a null context that doesn't actually encrypt the data, but that's usually just for testing. This is me saying I actually want to encrypt the data. And then I generate a key pair. So I generate the private and public key. And then I say, OK, encrypt this array of 1, 2, 3, 4, 5. Encrypt this array with my key, right? So the context kind of is managing both keys. It knows which one to use for encryption. And just to show you that I am encrypting things, crypto demos are sometimes hard to convince people you're actually doing the thing, right? Because I just gave you a number. You don't know what that means. But anyway, I'm gonna try to show you anyway. So let's see. What did I do wrong? OK, there we go. So I had Palisade saved to the disk, like the actual encrypted values. So if we look at what Palisade puts to disk, it's actually all this meta information that I was saying it was keeping track of. And let's see if I can find it. So here's the vector values. This is encrypted 1. So this is the integer 1 encrypted in this system. Now, you may wonder, why are you using so many bits to encrypt integers? Well, the reality is, because of the way FHE works, you want kind of more space. And that allows you to run more computations before you have to re-encrypt. Again, I'm being a little hand-wavy, but basically, we want to encrypt these as largely as feasible. But that's the integer 1 that's been encrypted with my public key. OK, so back to the Julia code. Now, this is because of a current limitation of our framework. But we have a function, and all that function does is sum whatever its argument is. In the future, we'll be able to pass sum directly. And usually, we can pass functions directly. But because sum is treated specially by Julia, we kind of have to wrap it in kind of a user-defined function. But that's not true in general. And then we need a dictionary that points to the types for these things. So here it's saying the function f expects this argument type. And then we tell FHE to evaluate f, which is just a standard Julia function, right? There's no magic there. Using this context, using the encrypted values, the ciphertext, and then use this dictionary to find out the types of things. So in this REPL, all I've done is load that file. So I have those things available to me. So this is the ciphertext, which we're storing as a bunch of pointers to things, but the actual things are those huge encrypted values. And we have the result, but the result is encrypted, right? If I wanted to see the actual value of the result, I would have to say, OK, decrypt this value in my context, right? So, and now I know that the sum of 1 to 5 is 15. But if I had kept, as long as I was good about keeping my private key actually private, no one would have been able to determine that except for me here with my private key. So that's kind of the power of fully homomorphic encryption. And again, I alluded to program equivalence. So that's actually something we are capable of doing. So we have linear regression, different versions of linear regression we've written, and we can test that they're equivalent. And we can make sure equivalent. And we can make sure, so for example, we wrote like a wrong version of linear regression, and our test suite makes sure that our system actually says, no, these are not equivalent. So it is possible, and we do it with the symbolic execution. OK, back to slides. OK, so I want to kind of talk a little bit about some of the challenges we've had in working with Julia, because I know some of the Julia devs are here, and I don't very often get to force you to listen to them. So here we go. So dynamic types and overloading, it's one of Julia's strengths. It does make it harder for symbolic execution, and I'm not saying that needs to change or anything, but it's just something, the kind of convenience for programming makes it very difficult to reason statically about things. And in symbolic execution, kind of what you're trying to do is do as much work statically as you can, so you can get these circuits. So that's a challenge. And overloading similarly, right? You have all these different methods with the same function name, and now you're trying to symbolically execute and determine, like, well, which one do I mean, right? And do those methods necessarily compute the same function? And the answer in general is no. So read eval is really, like this is, we don't have a solution to this yet. Hopefully we will, but basically, what does it mean to read or eval Julia, like the metaprogramming stuff, when you're symbolically executing? I don't know. I don't think it is. So that's something worth thinking about. And then this is the really big one. So this is the one that if we could snap our fingers and change one thing, there's no formal spec. So currently what we do is really hacky, right? We ask the Julia REPL, hey, can you please serialize the AST and send it to us so we can generate the circuit? And what we'd like to do is have a grammar of what an AST looks like and know that there are certain invariants or whatever. And that currently is not the case. Now, I know I'm saying this and Julia's not at version 1 yet, right? So it's kind of more just something to keep in mind. If any of you are ever thinking, hey, we're nearing version 1, and should we have kind of a more formal description of how these things work? We're begging you, yes, please do that. Symbolic execution tools, so even forgetting FHE, symbolic execution tools are really, really useful for generating test suites, for reasoning about program correctness. And they're much easier, it's much easier to write tools that work over programming languages if you have an idea of the semantics or the kind of abstract syntax of that language in a little bit more formal of a kind of document. So those are the big three things I just wanted to harp on a little bit. But yeah, so symbolic execution outside of FHE is kind of what I said. There's a really great tool called CLE for C, and it's already used on lots of open source projects. It's found like 20-year-old bugs in the GNU core utils. Symbolic execution is just a really powerful idea in general. And it'd be great if we could provide Julia with kind of a really robust symbolic execution tool. And another really big symbolic execution tool is Microsoft Sage, and they use it on all of the new security software inside of Microsoft. So it's just a really powerful idea, and we would love to be able to provide that to the Julia community. But currently it's a bit hacky because things are less formal than it would be nice for symbolic execution. Okay, and I have some acknowledgements. So the New Jersey Institute of Technology for Palisade, it's quite an engineering feat that they've accomplished. FHE is no simple task, and they've made it as simple as possible, and we were able to use it programmatically, which is pretty great. The Crucible team at Calwa, so I'm not on that team, but they kind of made this symbolic execution engine, and they made it as generic as possible. So even though they designed it for LLVM, we were able to kind of tweak it enough to use it for Julia, or as much of Julia as we currently can. And then the Ramparts team that I'm on have been great. We've only been working on this for about 6 months, and it's pretty amazing how far we were able to get, mostly because this team really knocked it out of the park. Okay, any questions? Yeah, oh wow, all right. Good. Yeah?
We get back to these lines, maybe you noticed that
yeah, did you notice the bug?
I didn't notice the bug. I was asking a question about
Oh, okay, right. Oh, this one?
This is the Julia.
Oh, the Julia example. Oh, that's over here.
Yeah, so it's, so that's what then.
Yeah.
So if I change the input, let's say I go 1, 4, 4, 5. So the answer is
Okay. No.
So now the question is how much of the details there get leaked in the answer?
Oh, that's a very good question.
It's more FXC.
Yeah, yeah.
But I know it's going to be incorrect.
Yeah, that's a very good question. So we don't actually have the hard quantitative information flow numbers on the amount of leakage that occurs. It's actually an open problem in general, but currently we have very good reason to believe that it's much, much, much less than otherwise. It is a fair question, and it is an open problem in general. Yeah. Yeah, right here. Oh, yeah, you.
So I have a couple questions. Sorry about that. The first one being, is most of this open source? Are you planning to open source this?
Yeah, so at Gawa, we try to make everything open source, and this is no exception. Currently, Palisade, so I had some links up in the acknowledgements. And so currently, Palisade is planned to be open source, and they have a Git repo that they do allow the public to look at, but you have to contact the head of the group currently. But they're planning a release sometime this year. But everything else is already open source and on GitHub.
Second question is for the symbolic execution. Are you working on the type representation or the service representation?
We work on the typed representation. So actually, we use is it code lowered or code typed?
Code type.
Yeah, code typed to kind of serialize it a bit for us already. And then we convert that to S expressions and send that over the wire, which, that's already a lot of legwork that we're saved from, right? But yeah, we use the type level.
And the third question was what the security assumption of the underlying crypto is. Is it LWE with bootstrapping, or is it something else?
So I'm not the crypto expert on the project. The crypto people have said bootstrapping a lot, so I'm going to go with that, yeah. Yes?
After the data is computed, it stays in the encrypted form. And how is somebody able to turn that into a diagnosis in the encrypted form?
So let me make sure I understand the question. You're saying if I have my encrypted genome, how would they be able to tell me if I have a disease based on just this encrypted data? Well, they would have to put that function that computes that over unencrypted data through our system. And that would result in a circuit that would tell them that over the encrypted data. Yeah, okay. And yeah, oh, yeah.
So related question, are there any restrictions on what this function f can mean?
Yes.
And it has to be pre-specified for encryption? Or?
So it doesn't have to be. If you know which functions you're going to run over encrypted data beforehand, you can encrypt your data in a way to make those functions more efficient. But that's not a requirement in terms of whether you can get a result. As for your first question of are there any restrictions on F, in order to generate a finite circuit, the computation must be finite, right? So that means we automatically lose things that are like while one, do this loop. You can't represent that as a finite circuit. So there are definitely restrictions on F. Yeah, follow?
So in the genetics example, one of the things that people might be interested in is the function f might be all possible subsets of the genome.
Right.
Which is pretty large. Would that fit into your encryption scheme? Would that be something that is feasible?
So it may take a very, very long time to run, but yes. Yeah. And do we have time for more questions or?
Yeah, we have time.
Oh, okay, great. Yep.
So just like when you make encrypted data, you only need the public key.
Right.
That's also true for making all the circuits.
Actually, for the circuits, you don't need to know either key. So do you want to see what a circuit looks like? You didn't say yes, I don't think, but I'll show you anyway. So that function f that just computes a sum, it's going to be a really simple circuit, as you can imagine. But this is all it looks like. Like the circuit itself isn't encrypted. It doesn't have to know anything about either of the keys. It just says, oh, okay, this thing took 4 inputs. It summed them together, and then it has a single output. The way to read this is the numbers on the left represent wires in the circuit. And so this is saying the output is the wire 5, the 5th wire. That's the output. And so you could send that to whoever has the encrypted data. They would run it. run this circuit on the encrypted data, and they could send you back the result. But whoever generates the circuit doesn't have to know about the keys. Yep.
Just, this sounds wonderful. What has any testing been done on what the performance impact of, say, you have it,
Yeah.
running it on encrypted data versus unencrypted data?
Yeah, the performance is atrocious. Yeah. Yeah. It's very much how much does privacy mean to you? Yeah. In terms of like hard numbers, I mean, I could show you some numbers, but they're on smaller like linear regression examples. In terms of scaling it up, we're limited by how much of the symbolic execution can deal with Julia, right? So that's our current limitation on that. But it is bad, right? Like even on the simple stuff, yeah.
And is there things that you've seen already that you could do to at least narrow the gap somewhat in the future?
Absolutely. So because circuits are inherently parallel, there's a big low-hanging fruit right there. We haven't explored that yet, though. We're good? Oh, do we have time? Oh, last question. Okay.
So you're saying that the ciphertext needed more space to do the computation.
Yeah.
How does that space scale with the size of the circuit?
Okay. So can you say that again? I'm not sure I understood.
Okay, so you're saying that the ciphertext representation has extra space in it.
Yeah.
To allow computation to happen.
Right. Right.
I'm asking how does that space scale with the size of the circuit?
Oh, I see. So I'm not sure of the actual kind of correlation there. What I do know is that systems like Palisade are able to kind of re-encrypt if they're running out of space as they go through the computation. So if a circuit is very long, where you might be running out of space in the ciphertext, the FHE systems are able to know that and re-encrypt if they need to. You just want to start big, so you only do that if you absolutely have to. Yeah. Okay. Thanks, everyone.